Okay, today we're going to do MRI Lecture 4. The topics today are going to be, we're going to finish our discussion of sampling, aliasing, and resolution. And then we'll talk a little bit about RF excitation and slice selection. So from last time, we talked a little bit about how in image space, the parameters of interest are the field of view in the x direction and the field of view in the y direction. Basically, those are determined based once you know what the size of your object is, you would put in those fields of view. And then you're typically going to want some sort of resolution. So delta x and delta y, this is sort of how finely you want to be sampled in image space. Once you've determined those parameters, and those are basically what you want your image to look like, then the FOV parameters will determine the delta K, and that tells you how finely you have to sample in K space. And as we'll find out today, the delta X parameters are going to end up depending on these WKX parameters. So essentially, the W parameters are how far out in K space you want to go, and the delta K parameters are how finely you want to sample in K space. So in terms of the relationship between delta K and FOV, we came up with what we call the Nyquist conditions. And essentially, the Nyquist condition is the condition such that the replicas in image space don't overlap. And so we found out that the requirement was that 1 over delta K had to be greater than FOV. Similarly, we can write this as 1 over the FOV, okay, is greater than delta K. And so this was one of the quiz questions that was had, which is essentially, you notice that delta K has to be less than some number. So if delta K is too large, we're not sampling K space finely enough, and that's what leads to aliasing. And so one of the quiz questions was, one of the answers then would be sort of, you don't want delta K to be too large, okay? And that allows us to avoid aliasing. Now, typically for any of the homework problems or design problems you might have to do, then we can simply set delta K equal to 1 over the field of view. And in that case, so one of the quiz questions you had was, what are the delta Kx and Ky parameters for something rect x over 4 and rect y over 4? And in that case, for example, if the FOV in the x direction was 4, then delta Kx would simply be 1 over 4. Okay, and so if you just follow that logic, that would give you the right answer for one of the quiz questions. And then the other thing that we talked about was simply the spacing of the replicas. And so essentially, as you see, the replicas in image space are just spaced by 1 over delta K. So if you're given delta K, then the spacing of the image replicas, so the spacing of replicas is just 1 over delta K, right? And so if you applied that formula, then that would give you the correct answer in the quiz as well, right? So there were 5 questions in the pre-lecture quiz. 3 of them, those were the 3 that were fairly straightforward. Before I go on, any questions about any of those concepts? Okay, so there's no questions about those, then I'm going to spend a little time on, there were 2 quiz questions that were a little harder for people, including one where most people did not get it correct. And so let's take a look at that. So let's consider 2 spins. So the question is, you have a spin at 0 and another spin at 0.5 centimeters, right? And you are looking at these spins every delta t of 1 millisecond, okay? And you're applying a constant gradient. And so these spins are evolving in the presence of a constant gradient. So the question is, the spins start off in phase. And so if what is the largest gradient amplitude that you can use such that the spins will not appear to be aliased? And so you're given some choices there. So one way to think about this is if I'm only looking at these spins once every millisecond, then if the spins, so this spin here at isocenter always stays at phase of 0. Okay, so that's not going to change. So all I really care about is this spin here. So if it returns back to its original position every millisecond, then we won't be able to tell that spin apart from the spin at 0. So delta t is 1 millisecond. So that means that if the spin is spinning with a frequency of 1 over delta t, or 1000 hertz, then at that rate, there's not going to be any sort of, we won't be able to tell that spin apart, okay? Because every time we look at the spins, it will have returned back to normal. So this is time. If it's processing at 1000 hertz, then it will do one cycle every millisecond. And so it's always going to appear at phase of 0. Okay, so it's being at phase of 0, 2 pi, 4 pi, 6 pi. So integers of 2 pi, such that it will always be back to its original starting position. So, so let's figure out what the gradient amplitude is for 1000 hertz. So we'd have gamma over 2 pi times gx, or g times 0.5 centimeters. That's going to give me my offset frequency. Okay, so I have 4000 times 0.5 times gx equals 1000. Okay, so this gives me 2000 times gx equals 1000. So we know if gx equals 0.5 Gauss per centimeter, then that is certainly going to be a value where the spin returns back to its original position every time. And so that will appear to be alias with the spin at isocenter. So we know we need to go below that. And all the numbers higher than 0.5 are multiples of that. So those would also give frequencies that would return back to normal. So let's assume, let's say we pick gx equals half of that. So the only other options were either half of 0.5, which is 0.25, or a quarter of that. So let's say we pick gx equals 0.5 Gauss per centimeter. In that case, the delta F would be 500 hertz. Okay, and then each time the spin is going to go 180 degrees. And so in that case, if the spin started in sync, then at every delta t, it's going to appear in a different, it's going to do 180 degree flips every delta t. And so therefore those spins will not be aliased. Okay, so that would be a reasonable choice. So let's say this is 0.25 centimeters. So we halved it, then we would get this delta F. All right, so are there any questions about that problem? Okay.
Wasn't 0.125 also an option?
Yes, but it asks you what is the largest amplitude that can be used.
Oh, okay.
So
okay.
0.25 is greater than 0.125. So, but that's a great question. Yeah, because it's multiple choice. Yeah, go ahead.
They're aliased every other millisecond, or because
aliasing. Yeah, aliasing just means they look the same over time. So okay, it's if you have two people if you're like looking at two bicycle wheels and every time you look at them, they look like they're exactly the same position, then you would say they're aliased.
Okay.
Yeah. Okay. Great question.
Yep. Got it. Thank you.
Okay. Anything else before we move on? Okay. So the other question that people, a little bit over half got right, was this question, which is basically last time we talked about where k-space, where we are in k-space is determined by gamma over 2 pi, the integral of the gradient, the gx gradient, dt, and ky of t equals gamma over 2 pi, integral of the y gradient. Okay, so we know that where we are in k-space is simply related to the area under the gradient. So you're given this problem here where we want to move out to this point in k-space of 0.1 and 0.2 inverse centimeters. All right. And so the question is, we have a gradient amplitude G max equals 5 Gauss per centimeter. And so we want to say what's the minimum time required to move out from the center of K-space, so from the center of K-space out to this point in K-space. So we want to go out there as quickly as possible, and so we want to figure out what that minimum time is. So that minimum time is going to be determined by getting out to this point, because that's farther out. It's going to require a greater area. So in terms of doing this problem, we need to look at that. So we say we want to get out to 0.2, and to do that, we have the 4,000 hertz per Gauss times some gradient times dt, and this is 5, right? So it's 20,000 times some delta t that we want. And so to go from 0.2 to 10,000, you just have to multiply by 1, 2, 3, 4, 5, 10 to the minus 5. Okay, and that will get you what you need. And so in that case, 10 microseconds was the correct answer, and so most people, I think, got that. So some people chose 5 microseconds. That would get you out to this point, right? That would be enough to get to 0.1, but it's not enough time to get out to 0.2. And so in that case, when you have two, if you're trying to get out to some point in K-space, it's always, the minimum time is always going to be dominated by the one that's further out K-space. So that's what you'd want to take into account. So on the homework, next homework, you'll be seeing some problems that sort of will make use of the concepts that were covered in the pre-lecture quiz. So hopefully that'll help you. And then we'll go over some more problems today as well. That should be useful for your homework. All right, any questions before we move on into the material of this lecture? All right. So what we're going to talk about next is windowing. And so windowing in K-space just means that if we have some Fourier transform, right, you know, the Fourier transform goes off to minus infinity and plus infinity. And so we're not going to, in general, want to spend the time to acquire all that data because, you know, in general, we want to acquire the images as quickly as possible. Certainly in an emergency room case, you're always concerned about, you know, getting the patient on and off the table as quickly as possible. And so the idea is we only want to acquire some part of K-space. We want to acquire the minimum amount of K-space required and then just make our image from that. And so the way we represent that is if this is all of Fourier transform, we can multiply by some windowing function, and that will give us a windowed Fourier transform. Okay, so it's basically 0 everywhere else except for the part where we want to keep. So this is a multiplication in the Fourier domain, so it leads to a convolution in the image domain. So we'll have our object, that would be our ideal object, convolved with the inverse Fourier transform of our windowing function. And this would give some image that is related to the ideal image, but is obviously going to be affected by the convolution with the window. So this gives you sort of a sense of what the effect of that is. So let's say this is my object, my ideal object, and this is its Fourier transform here, which is a two-dimensional sinc function. So if we apply a windowing function here, such that this is a rect function in K-space. So that's a rect function. And so now we're left with here, it's 0 everywhere out here, right? These are all zeros. And so we're only left with the part of the Fourier transform that's within that window. So the inverse transform of the rect function is just a sinc function. So it's going to say we take our original object and we convolve it with the sinc function, and that gives us this blurred version of our original image. All right. So in general, when we window in Fourier transform domain, we're getting rid of the higher frequencies, and so we'll end up with a more blurred version of our image. So typically, a very common choice of windowing is, at least for this, the one we'll start off with because it's simplest, is the rect function. So we're simply going to have a rect function with the width of wkx in the kx direction and wky in the ky direction. So if I take the inverse transform of that, I simply get this sinc multiplied by another sinc, and with these scaling terms out in front. So it's going to be my ideal object convolved with these two sinc functions. So one very useful thing is to look at the effective width of what a sinc function is. And effective width is basically just the area over the height. Okay. And as you saw in your homeworks, you can get the area very simply by taking the Fourier transform at the 0th frequency. And so it turns out we can solve for this, and we find out that the effective width of a sinc function is simply 1 over WKX. So if I have a sinc that's, if I have a sinc function of this form, okay, this has its first 0. So this is sinc WKXX. It has its first 0 at 1 over WKX. All right. And so the effective width of that sinc function is essentially just that. That distance there is also 1 over WKX. And so if you, as long as you remember where the first 0 of the sinc function is, you can take that as the effective width of the sinc function. So it's saying that the area of this sinc function in blue is the same as the area of this rect function, the square function that has the same height. And so that's the effective width of a sinc function. And so essentially, you can sort of see that as I make this WKX larger, as I go farther out in k-space, right? I collect more and more k-space information, then my sinc function is going to narrow, because 1 over WKX is going to get tighter and tighter. And so that means my effective width is also going to be tighter as well. And so that makes intuitive sense in the sense that, the more data I collect, then the sharper my sinc function should be. It should have much smaller effective width. So we can think about resolution and spatial frequency. So if I have a window of width WKX, then that means the high spatial frequency. So basically I'm going over some with WKX, right? So that means this high spatial frequency here is WKX over 2, and this is over at minus WKX over 2, right? So the high spatial frequency that we can actually capture is WKX over 2. Right? And this corresponds to a spatial frequency of 2 WKX. So imagine if you had, so that would look like a sinusoid like this. So this is a sinusoid with period of 2 over WKX. And then just that half of the cycle is just 1 over WKX. So that's the effective width of that function. So essentially, if I can sort of, if I have a frequency, the highest frequency component I have is this sine function that goes up and down every 1 over WKX, and that's the highest sort of effective width or resolution I can have for my image. Okay, that's an image that goes sort of from blue to white to blue, that I could potentially represent with a sinc function or a sine function that looks that goes up and down with that spacing. So that's another way of looking at why we would pick the effective width to be that. The other way you can think about effective width is that the effective width is set up such that if you have 2 dots and you convolve them with sinc functions. So if my original object had 2 Dirac delta functions, okay, that was my ideal object. After I convolve them with sinc functions, they're going to each get blurred out, right? And so we want to pick the WKX just such that that we can just differentiate the two right at the border of where we can no longer see that they're different. So you can sort of see here, if I pick large values of WKX, like 2 or 1.5 in this case, those 2 objects are clearly distinguished, or with enough SNR, you can sort of see that there are 2 potentially peaks there. Once I go to my limit of WKX, in this case, 1 is sort of what I've said here to be the limit, then at that point, that's exactly where those 2 sinc function peaks merge together, such that there's only 1 peak. And so that also sort of gives you some insight into as you go farther out into k-space, you have enough information such that you can differentiate two peaks from each other. Okay, so putting it all together, what we have in the decisions we have in MR look like this. So this is, let's say this is our object. Okay, and it has some Fourier transform, which we're assuming that's sort of the ideal Fourier transform. One thing we do, obviously, is we sample in k-space. Okay, with some spacing delta kx, delta ky. So that's a multiplication in k-space. So that leads to a convolution in object space with these cone function with a spacing 1 over delta k. Okay, so this leads to replication of our image. Okay, and if those replicas are too closely spaced together, then that leads to aliasing. The next thing we do is we window in k-space. This is also multiplication in k-space. All right, and so the windowing is just saying we're not going to collect data from all of k-space, we're only collecting a certain portion of k-space. So this leads to also convolution now with this sync function here, and this is what's going to lead to blurring. So it's those both effects together. So in the end, we have this is sampled and windowed. Okay. And at the end, we have replicas and they're blurred. All right, so that's what we end up. And so the idea is we want to design our MR system such that we have the replicas are not overlapping, so we avoid aliasing, and also the blurring is such that it's low enough such that we feel like we have the resolution we want. This is just sort of the summarizing what we have in mathematical terms. So we multiplied by a cone function and a rec function. Therefore, we convolve with a cone function and convolve with a sync function. Okay, so essentially, then the design equations come down to this. So these are the design equations we talked about last time, where we have the delta, given that once you know the FOV of x and y, then you can figure out what the sampling is, the delta kx and the delta ky are. The other thing that you'll typically determine, you want to know what the resolution is, right? You want to determine some resolution. And so this resolution is what we call sort of also is related to the effective width. Okay, that's sort of the sampling, the smallest sort of sampling cell that you can consider in your image. And so that is simply 1 over the width. And so, for example, if I'm given the delta y or delta x, then I can easily figure out that delta kx, for example, equals 1 over delta x. So for any problems you have, you're sort of going to go by these equations, which are the sort of the governing equations for the sampling in MR. Okay, so to sum up, what we have is as we said before, the delta kx's and delta ky's are determined by the FOV, okay, and then the widths are determined by the resolution. Okay, so one thing we can look at as a sanity check is we can say, okay, well, how many samples am I acquiring in k-space, and how does that compare to sort of how many voxels I have in image space? So we can write down, for example, if I have an FOV of x and a resolution of delta x, and that means I'm going to have FOV of x over delta x samples in my image space, right? Because I'm going to have, if I think about this is a delta x, there's FOV over delta x of those samples that I'm going to have in image space. All right, so that's FOV over delta. But I can write FOV in terms of as 1 over delta kx, and I can write delta x as 1 over w kx, all right? And therefore, I can write this as w kx over delta kx. And w kx over delta kx is just how many samples I have in Fourier space, right? So w kx is the width, and delta k is the sampling period. So that's how many samples I have in Fourier space. So there's sort of this nice relationship that the number of samples in Fourier space equals the number of samples in the image space, right? And so that's just a nice sanity check you can do. Okay, so doing that, we can sort of write out what sort of the consequences of that. So we've looked at this term quite a bit before, this e to the minus j 2 pi kxx, and that's assuming we have continuous objects. So kx is continuous, x is continuous, and so everything we've done up to now is continuous. But as you've done in your MATLAB exercises, when we go to simulate these things, or when we actually go to compute images, we're doing everything on a discrete grid. All right, so instead of kx, we're going to look at things that are multiples of delta kx, right? Instead of x, we're going to look at things that are integer multiples of delta x, right? And so what we can do is we can simply plug these in for our x, our kx, and our delta and our x. And then we notice that we realize that delta kx is just 1 over FOV of x. And then FOV of x divided by delta x is just n of x. And so that gives us these complex exponentials that are just e to the minus j 2 pi mn over nx. All right. And it turns out this is just one of the roots of unity. So if you remember back to sort of taking the square root of 1, complex square root of 1, that is one of those square roots. And so if we have that, then we can say that the Fourier transform at any one of those discrete values is equal to g of x. So this is in continuous time, okay? But now we've replaced the kx with our delta kx. And then we can approximate this integral as a sum. So we're taking discrete values of our object and multiplying it by this term here, which is this term here. And I've included this delta x just here as sort of an integration factor, but in general, we don't sort of take that into account. It's sort of understood that the value we get is sort of the integral over some spatial volume. But this is essentially the FFT, or for the DFT, the discrete Fourier transform that, for example, like MATLAB will compute for you. Okay, so that's sort of one way of looking at going from what we've been talking about, which is sort of talking about real objects, into what happens when we actually have discrete objects. What do we do there? Okay, so one of the consequences of that is that typically when we do MR, at least traditionally, and it still holds to this day, is we typically do a power of 2 or something that's an even number of samples. Early on, this was to sort of take advantage of fast reconstructions when FFT algorithms were really limited to powers of 2. Now it's a little more flexible, and there are fast algorithms even for other integer value, sort of other values. But early on, that was a big concern, was going quickly. But one consequence of that is, for example, here we want to do 4 lines in k-space, right? And the argument is we only need to acquire these 4 lines in k-space, and we don't need to acquire this line. Okay, and you might think, well, aren't I missing some information by not acquiring this line? And it turns out you're not, because, for example, if we picked, remember we have in our discrete time, we have e to the minus j 2 pi mn over n. Okay, so we simply replace this by n over 2. We find out that whether we do n over 2 or minus n over 2, so this would be, for example, at n over 2, and this would be at minus n over 2, they both give us something that's e to the minus j pi q, which is just going to go between like 1, minus 1, 1, minus 1. And so because of this, how the sampling is set up, that those 2 far points in k-space essentially give you the same information. And so therefore, that's one reason why you'll see sometimes people don't necessarily collect symmetrically around the axis there. Okay, so let's do a problem. We'll do this one together so that this will help set you up for the homework. So the question is, you consider an object g of xy equals cosine 2 pi 3x plus 2y times rect x over 3 rect y over 4, right? So the question is, what would be reasonable choices for the resolution of this object? And And also, what are the KX max and KY max parameters needed to achieve this resolution? All right. So let's think about this. So first of all, we can look at this as a cosine 2 pi 3x plus 2y. Okay, so let's look in the x direction. So in the x direction, so the frequency here is basically kx equals 3, and the frequency here is ky equals 2. All right. So let's sort of draw out the x direction. So if I think about, for example, a cosine, right? So this has period of 1/3, right? Okay. And as we said before, or we can sort of think about, we really only need a sort of a reasonable choice for resolution is half of that period, because, if something is varying between plus and minus, then that's a reasonable choice for the resolution. So taking half of that, so 1/6 would be a reasonable choice for the resolution of that object. Similarly here, if I drew this has a period of 1/2. So reasonable choice of resolution would be 1/4, okay, which would represent sort of the width of one of those lobes would be 1/4. Okay. So therefore, we know that WKX equals 1/Δx. So that would be equal to 6 inverse centimeters. Okay. And KX max is equal to WKX/2. So that would be equal to 3 inverse centimeters. And you can do the same thing for this KY max would be 2 inverse centimeters. Okay. So that's one way you can do it. The other way you can do it is you can just look at the highest frequency that you need to be able to capture is 3 and 2. And so those are also would be another way of figuring out at least this part of the what the KX max and KY max are. Okay, so are there any questions about that problem before we move on? All right. So in terms of how these things play out in an MR, so this is a picture of an MR acquisition panel that from a GE scanner that you might see. So you notice here, for example, one of the things that we have to specify is the FOV. All right, in this case, this is set to 24 centimeters. The other thing you'll see here that we'll talk about in later in this lecture is slice thickness. And so here they're asking for, in this case, it's 5 millimeter slice thickness. And then in this thing, they also specify the phase FOV, and this is just a multiple. So this would be, for example, the FOV in the X direction, and then the phase would be FOV in the Y direction. And that's just a multiple of the FOV in the X direction. So in this case, it would be a 24 by 24 FOV. And then they don't specify the resolution here in terms of centimeters and millimeters, but what they do specify is how many points they want. So for example, in this case, delta X would just be 24 over 256, okay? And delta Y would be 24 over 128. So that's how you would go about specifying, for example, these steps so whenever the operator, the radiological technician sits down and specifies these parameters, then behind the scenes, the software calculates how to actually run the MRI pulse sequence. And so we'll talk a little bit about that in a bit. Okay, so just to recap from last lecture, we talked about how sort of the most common sequence that's used is the spin warp pulse sequence. And what it looks like is we're essentially going through K-space line by line by line by line. And what it typically is done is we will do this every time we have an RF pulse, we excite some magnetization. we read through one line of K-space, we wait some amount of time, TR, which is the repetition time, and then we come back and we acquire another line as K-space. And we repeat this process over and over again until we've acquired all K-space. Now, the selection of TR, you might think we always want to go as quickly as possible. It turns out that that is not the case, and we'll find out in the later lecture why sometimes you want to pick TR to achieve a certain image contrast. And if you pick TR too long or too short, it also has consequences. So there are some limitations that we'll talk about. But for now, as we're talking about the imaging process, just know that in the spin warp, we're going through line by line by line. So this is another picture of that. And just to remind you what's happening in, so we're looking at Kx and Ky. These gradients are the same. So these are what's known as the readout gradients. So Gx by definition is the readout or frequency direction. So whenever you hear the term readout or frequency, by definition, we're talking about Gx. Now that's a logical x-axis. So it's not a physical x-axis, but just by convention, when we talk about Gx, that's what we mean. And then the phase encodes are by definition what is referred to as what's happening on the logical y-axis. So since the Gx gradients are the same on every repetition, you'll notice that the trajectory through K-space is the same. So we always go out to some negative point in K-space and then slowly traverse back along the rest of K-space. So we go from some negative point in K-space to a positive point in K-space. So we're going line by line by line. The Ky phase encodes, you'll notice, and we talked about before, are different from shot to shot. So that provides us a different offset and gives us different lines of K-space on each shot. And so you notice in Ky, we go off to some negative value, and then we just hold that value. And then we go on the next shot, we come to some other negative value, and we hold that value. And then here, it's a 0 value. Now we're going out to a positive value, holding it, going out to a farther positive value, and holding it. And so that's basically showing you how from shot to shot to shot, we are acquiring different lines in K-space. And the K-space trajectories reflect that. Okay, so we're going to talk a little bit about how to actually practically design a spin warp pulse sequence. Just to preface what's going on here, this is going to be a specific application of the design equations that I gave you for delta Kx and delta Ky and Wkx, Wky. So we're going to do that specifically for the spin warp pulse sequence. Now, in your homework assignment that's coming up, you're going to be given some other trajectories. And so you want to still apply those basic concepts. But one warning is don't try to apply what we're doing right here in terms of the specifics of the spin warp pulse sequence to those other pulse sequences, because that won't work. And that is something that people try to do. It will just confuse you. So just use this as an example of how you would apply those basic principles to one pulse sequence. And then for the homework assignments, you'll sort of think about how you would generalize that to other pulse sequences. All right, so that's just something to keep in mind as you're doing the homework. So let's talk a little bit about sort of how sampling actually gets done. All right, so when I have my signal, so this is the MR signal that's coming right off the scanner. The first thing we typically do is we demodulate it. All right, so we're basically getting rid of that constant omega naught term. And so for those of you for electrical engineers, this is sort of like mixing down to baseband. Okay. Now sometimes there is a mixing down to intermediate frequencies, but for the purpose of keeping things simple, we are assuming we're sort of essentially taking everything from the laboratory frame down to the rotating frame by getting rid of that sort of overall e to the minus j omega naught t term. So there was always that term, and now we're just sort of multiplying by e to the j omega naught t to cancel out that term. All right. Then typically there'll be a low pass filter that we'll talk about later. And then here is where the sampling gets done. So we're taking the ADC, stands for analog to digital converter, and it quantizes and samples. So it converts our continuous time, continuous valued signal into something with discrete values. So that's quantization. So this is going to be analog to digital converter. Okay, and typically it does two things. It quantizes and it also samples. Okay, for this class, we're really going to focus on the sampling. So it takes one sample every delta t. All right. So as the signal is coming in, we're getting a sample of that every delta t. So that's going to represent our sampling in the kx direction. So remember, we're moving through k-space as the gradient odds in time. As we do this, we're sort of moving in k-space. We're crossing a trajectory in k-space. All right. So essentially, if this is kx versus time, we're acquiring one sample of the signal as it's coming in and moving across k-space every delta t. All right. So the question is, how far do we move in k-space every delta t? And that's just given by delta kx equals gamma over 2 pi times gxr, which is the amplitude of the readout gradient, times delta t. So typically the design equation will be as such. You're going to typically be given FOV of x. You're going to figure out what the delta kx should be. And from that, based on the pulse sequence, you're going to figure out some other design parameters. In this case, you know, if you're given delta t, you might figure out gxr. Or in the other case, if you're given gxr, you might figure out the delta t. Right? But the key always comes down to, as you're applying this, you're always starting off with what is delta kx, and then figuring out, you know, how delta kx is expressed, and then figuring out what you should set that equal to. So here's an example here. So let's say my FOV is 25.6 centimeters in both the x and y direction, and the delta x and delta y are 0.1 centimeters in both directions. Right. So I simply want to set FOV of x equal to, this is my delta kx, right? And so I've combined everything into one. You can do it in steps if you want to. And so from there, I can, and here I'm given delta t. So I know FOV, I know delta t, and I just solve for gxr. And in this case, if I solve for gxr, I get this value here. So once again, typically you'll go from FOV of x to delta kx, and then you'll figure out some parameters from there. The other thing is the resolution in the x direction. And so the resolution is sort of how far I've gone out in k-space. And so remember, this represents, in k-space, we're going from here to here, right? So in k-space, we're going from some point out here to some point here, okay? So this would be my WKX. So if we're looking at the spin warp lines, then this is my, that's my WKY, and what we care about here is my WKX. Sort of how far is it from this point in k-space all the way to this point in k-space here. All right, so we know we have some resolution we're trying to acquire. So that will allow us to determine my WKX. And then WKX is simply going to be the area traversed under this part of the gradient, right? So just gamma over 2 pi times the readout gradient amplitude times tau sub x. Right. So here's an example. I think this is just the example where we had delta x equals 0.1 centimeters. Okay, so we know that this is here, right? This is my WKX term here, right? I'm told delta x. I know what gxr is for my previous solution, so I'm going to solve for tau sub x, how long I want the gradient to be out. Okay, and it turns out that in this case, tau sub x, if I plug in everything, equals 8.192 milliseconds, which actually turns out to be the number of samples, 256 times delta t. And so that's a way you can sanity check in terms of, you know that, for example, the FOV was 25.6 and the delta x was 0.1. So we know that the number of samples in an image space is going to be 256. So we better have the same number of samples in our readout direction as well, right? Okay, so we're going to do this. We're going to do two problems together, and then we'll have you guys in breakout rooms in a little bit. All right. So you're asked to design a spin warp readout gradient to achieve FOV of 20 centimeters and resolution equals 2 millimeters. The maximum gradient strength achievable is 2 Gauss per centimeter, and the readout sampling period is 5 microseconds. What should be the amplitude of the readout gradient? Pick the closest answer. So pick the closest answer means that the actual answer may not actually be listed here, but let's go through that. So we are told that the delta t is equal to 5 times 10 to the minus 6 seconds, right? And we can avoid this. We can sort of, we know the maximum gradient strength is 2, but that's not going to help us solve what the GXR should be. So we'll just put that aside for now. We know that delta kx should be 1 over 20 centimeters. Okay. And we know that we want that to be gamma over 2 pi times our gradient amplitude times our delta t. Okay. So what we have is this is equal to 4,000. And this is equal to 5 times 10 to the minus 6. Okay. So we're going to have GXR is equal to 1 over 20, 4,000, 5 times 10 to the minus 6. Okay. That equals 10 to the 6 over, what is that? That's 100, so 4,000 times 0, 0. So that's 1 times 10 to the 6th over 4 times 10 to the 5 equals 0.25 times 10 to the 1 equals 2.5 Gauss per centimeter. Okay, so in this case, the closest answer would be 2 Gauss per centimeter. But that's just an example of how I went from using the FOV to get the delta K, and then from that, calculating some parameters. All right, so the other thing we need to do is phase encode, which is sampling in the KY direction. And so in this case, we have these phase encode blips, they're typically called, or phase encode gradients. And typically we keep them all the same width. So each repetition, we keep that tau sub y the same. And we're just typically varying the amplitude. And so the incremental the increment with which we increase that amplitude, we'll call GYI. All right, and so that's how much further out we go in K space each time we do a phase encode. And so we know that, so we can say that delta KY is just gamma over 2 pi times that GYI times tau sub y. So typically you're given FOV of y, you can figure out delta KY, and then you'll solve for either GYI or tau sub y. Okay, so here's an example. So FOV of y, remember our FOV was 25.6 centimeters. Okay. And so we just set that this is equal to 1 over delta KY. And we're, in this case, we're just given tau sub y equals 4.096 milliseconds. So we're going to solve for GYI. And if we do that, we end up with this very small 0.00224 Gauss per centimeter phase encode gradient increment. The other thing we need to talk about is the resolution, right? So that's sort of how far we're going in KY space. And so from there, we know that we have some resolution delta y, and that's equal to 1 over delta KY. And so that's going to typically be given by, this sort of, all this area represents how far in K space I've gone, above, if this is K space here, KX, this part gets me out to some point here, and then this area would get me out to some area here, okay? So it's this total area here that represents my WKY. So what is that area? Well, that area, if the largest gradient I have is GYP, then the total extent is 2 GYP times tau y, which is the area. And then I just multiply by that gamma over 2 pi. So that's where this equation is from. All right, so let's do an example of that. So in this case, we're given their delta y, we're given the tau sub y, and we just want to solve for GYP. And if we do that, we end up with GYP equals this in Gauss per centimeters, and this just equals the number of phase encodes divided by 2 times GYI. So that's a standard HX. So the maximum amplitude I go out here should simply be the number of phase encodes multiplied by each of these little chunks, right? Okay, so what we have is we've totally designed our spin warp pulse sequence in the sense that the things that have to do with the readout, so the readout gradient depends on FOV of x and delta of x, and the things that have to do with the phase encode gradient depend on FOV of y and delta y. So let's do a problem together before I send you guys to the breakout rooms. So for a spin warp pulse sequence, you're asked to design phase encode gradients to achieve FOV equals 20 centimeters and resolution equals 2 millimeters. The maximum gradient strength available is 6 Gauss per centimeters. What is the minimum width you can use? All right. So we're trying to design a phase encode gradient, and we sort of want to go out, the maximum gradient strength we have is 6 Gauss per centimeters, right? And we want to figure out what this tau sub y should be. So this is really going to be determined by the resolution, right? Because that's for how far out in K space I want to go. So I can ignore the FOV for this problem and just consider what the resolution is. Okay, so so what we have is we know that the W K Y equals 1 over the resolution, which is 2 millimeters. Okay, which is equal to 1 over 0.2 centimeters. So that's 5 inverse centimeters. And so we know that we want WKY is equal to, if we want to span from here to here, then that's going to be an amplitude of 12 Gauss per centimeter. Okay, we have our gamma over 2 pi times tau sub y. Right. So we have 5 equals 4,000 times 12 tau sub y. So tau sub y will equal 5 over, what is that, 48 times 10 to the 3. And that's approximately equal to, it's 5 over 48 is about 1/10. So that's like 0.1 times 10 to the minus 3, equal about 10 to the minus 4. Okay. So that is pretty close to 100 microseconds. Okay, so that would be the minimum width we can use. All right, so are there any questions before I send you into breakout rooms for the next question? Okay, so the way we're going to do that, we're not going to use poll EV for this one. We're going to use the chat feature on this one. So what I'm going to do is I'm going to send you into breakout rooms. I'm going to read the question, and then I want you to discuss this. And then in the chat, you're going to, write down either your breakout room number or the names of the people in your breakout room, and then just sort of see which of these options would work. And the idea is that there can be more than one option. So unfortunately, we can't really use the Zoom poll feature for this one. So the idea is you want to consider spin pulse sequence to achieve an FOV of 24 centimeters in both the X and Y direction with 1 minute resolution in both directions. The maximum available gradient is 5 Gauss per centimeter. The user doubles the FOV in the X direction to 48 centimeters. What will you need to change in the pulse sequence? Assume that the ADC sampling rate, 10 microseconds, does not change and the resolution is held constant. And you may pick more than one option. All right, so I'm going to send you into breakout rooms now. You'll have about 5 to 7 minutes to do this. Okay, so please make sure to join the breakout room. Okay, so let's take a look at what people, I'm just looking at the answers that are coming in.
Are we supposed to see a poll right now?
No, people are direct messaging me, but I mean, I guess in the future I should have specified just direct message everyone. But
Okay.
yeah, just direct message the answers to everyone or to me. It doesn't really matter. We'll just, I mean, I'll get it. I have a transcript of the chat anyways. Okay, so let's take a look at this together. I think there is some diversity of answers. So let's go through this question together. So first thing is the user doubles the FOV in the X direction. Okay, so remember by default, the X direction is always what we consider the readout direction. And so X, remember, is readout, and Y is the phase encode direction. Okay, so since nothing has been changed in the Y direction in terms of GY or Y, then we can just right off the bat eliminate these as possible answers. Okay, so that's one thing to do, which would sort of simplify the answering process. The next thing is that the only thing they've doubled is the FOV has gone up by a factor of 2. Right? Okay, so basic principle, we know delta kx equals 1 over FOV of x, right? So if delta kx, if FOV goes up by a factor of 2, that means delta kx must go down by a factor of 2. So we know that delta kx has to go down by a factor of 2. Okay. We're also told that the delta t is the same, right? Right. And we know delta kx equals gamma over 2 pi times gxr times delta t. So this stays the same. This has gone down by a factor of 2. So therefore, gxr must also go down by a factor of 2. So that would mean that h would be correct, and this would not be correct because you can't have and double at the same time. All right, so h would certainly be a correct answer. So now we're left with sort of the number of the readout samples and the length of the readout samples. So we can think about the number of readout samples. So one thing to realize is the resolution has been kept constant, right? So delta x is the same, right? So we know the number of kx lines, FOV has gone up by 2. So this must also have gone up by a factor of 2. Right? So the number of samples, or the number of x lines, number of voxels has gone up by a factor of 2. But we know the number of k-space samples has to equal the number of x samples. And so the number of readout samples should also be doubled, all right? Oh, sorry, that's, well, it's C, right? And then E also, because if the number of readout samples has doubled, then the length of the readout gradient will also double because the sampling period is stayed the same. Right. So in this case, C, E, and H would be for this problem. So this is an example where you look at, FOV, and then from that you can sort of look at different parameters such as delta kx, and then the gradient amplitude. And so, okay, so are there any questions on this? There'll be similar questions on either upcoming quizzes or homework. So if you have any questions, now is the time to ask. Okay, I'll assume everyone's okay with that, and move on. Is there a question there? No. Okay. So I'm going to just talk. We're going to end this lecture with some few things, and then talk a little bit about slice selection, and then we'll have to pick that up again next Monday. So one of the things that we find out is we've talked about when we window our image, we end up convolving with these sync functions, right? So that means if we have a sharp edge like that, then we're going to be convolving that sharp edge with a sync function. And it turns out when you do that, you get these ripples. sort of this ringing artifact, and this is what's known as Gibbs artifact. So there's a couple of ways you can deal with that. So the Gibbs artifact is typically not desirable, and we'll see towards the end of the class how new methods from deep learning are actually dealing with this quite well these days. But for now, we're going to talk about a very basic image reconstruction is what would you do given what we know now about how to reduce those ripples. So one thing you could do is you could just go from a fat sink to a much narrower sink. So at least those ripples would die out much faster, okay? And so, for example, here you can sort of see going from 256 by 256 image to 256 by 120 images. This is in the case of this where we've increased the resolution going from here to here. And so you notice that these ripples here are now much faster in the high resolution image. So one way we can deal with these ripples is simply go out farther in k-space, have a higher resolution image, and reduce those ripples. Now, the trade-off there is you have to scan longer typically, and so there's a trade-off in terms of time versus image quality. Another thing you could do is you could, we've talked about using a rect function to window. So we have a very sharp cutoff, okay, similar to the Ram-Lack filter in CT, where we had a very sharp cutoff in Fourier space. So instead of a very sharp cutoff, you can use what's called an apodization window, similar to in CT, you saw Hanning windows and Hamming windows and other things like that. And so we can have a very smooth roll-off in k-space. So we generally weight the data in k-space. And so now instead of convolving a sinc function, you're going to be convolving with something that's a lot smoother. Okay, in this case, it's the Fourier transform of a Hanning window. And so what you'll see here is that there's a trade-off here. So this is here with the ripples, that's when we convolve with the sinc. And this is now convolving with a Hanning window apodized acquisition. So you see we've gotten rid of the ripples, but now there's a trade-off in the sense that this curve here, the sort of the slope is sort of not as steep. And so that edge is going to get blurred out. So we're going to give up a little bit of blurring of the edge to get rid of those ripples. And so there's a trade-off there. And that makes sense because we are essentially cutting off those higher frequencies much more quickly, those sort of intermediate frequencies much more. And so we're going to lose some resolution in the image. The other thing that sort of comes up quite a lot is that, we've talked about the field of view and we said, okay, give us some object, you're going to pick some field of view. And if you don't meet those requirements, then the image is going to be aliased onto itself. But what happens if you have something that's really big? So for example, let's say you had a snake that's really long, or you had a spine. So a typical clinical thing might be you're imaging this person and here's their spine, and all you care about is some little small part of their spine, okay? And yet the field of view here is quite large, right? And so if you have a large field of view, you have to have very small delta Ks, and so it's going to take a long time to go through k-space. So the question is there something else you can do to avoid having to have such a large field of view? And so it turns out that there's actually two solutions for that, and we're going to talk about both right now. One is just we always want to put the long direction in the readout direction. So here F stands for frequency, which is also the readout direction. Okay, so the idea is if you have an object that's very long in one dimension, then it's always advantageous to put that dimension as the readout dimension, all right? And why is that? Well, imagine you have, this is the readout direction, okay? And here's my object. And I'm applying a gradient in that dimension and it's the readout gradient in that dimension. So assume that in this case, I care about this part of my image. Okay, so I only want to have spins. I only want to see the spins in that part of my image. And so those spins are going to have some frequency bandwidth determined by the gradient. So this spin here spins faster. This is at isocenter. This spins slower. Okay, so let's say this is at plus delta F and this is at minus delta F. Okay, and something down here would be at like minus 2 delta F. And maybe this is at minus 3 delta F. Okay, So the idea is every spin is going to have a different frequency that it's coming in at. So what I'd like to do is I'd like to then just filter out those spins from areas I don't care about. And so that's actually what you can do in the readout direction. You can actually apply a filter that basically just gets rid of the electrical signal that's coming in from those areas. So basically we can filter out the signal that's coming from these spins. And so we don't have to worry about them in terms of the FOV. And so that's something that's done basically a standard practice in NMR, all right? So that's just an example. And so that's typically done here with the low pass filter part. So as the signal's coming in, you could low pass filter it and get rid of those frequencies that you don't care about and really only focus on those frequencies that are within your bandwidth of interest. So what that means is there should never be aliasing in the readout direction. You should always, basically, once you've set the field of view, the system knows to sort of filter out everything that's outside that field of view. Now, it's not a perfect filter. There is some roll off. And so you do sort of, at the very edges, there can be some aliasing still, but in general, it's a pretty good solution. Okay, and then in the last 5 minutes here, we're going to just set up some basic concepts for RF excitation that we'll then revisit on Monday. So as you may recall, the basics behind RF excitation is that we want to take spins from their equilibrium state and excite them to some angle away from equilibrium, and then they're going to let them process around. Okay. So the motivation here is also similar in the sense that, let's say you have some object here. Maybe you just want to image some axial slice here. And in this case, you want to just excite a slice and look at its cross-section in very high dimensions. So you'd like to find some way where instead of exciting all the spins, you can just excite a very small section of spins, okay? So this is a little different than what we just talked about. Before, we were assuming that all the spins are active and we're just filtering out the reception signal. Here, we're looking at how do you make it so you only excite some of the spins. Just to remind you, with slice select, with RF excitation, the key was if our B1 field is on resonance, then that's very effective at tipping the spins. So that's there. And then if it's off resonance, if we're not at the same resonance as the spin, then the RF pulse is really not very effective as tipping the spin away. So this is going to give us a clue as to how we design a pulse that can only tip spins in a certain region of space. This is just to remind you that we've talked about the laboratory frame and the rotating frame before. And in the rotating frame, in the laboratory frame, you saw the spin would spiral down. In the laboratory frame, that overall precession is gone. And so you just see the spin tipping over to the desired flip angle location. And reminder, precession, we have the log frequency equals gamma times B. Okay. So what I'm going to do is I'm going to skip over some of these parts here for now, and we'll we'll revisit those on Monday. But I want to just get set up what we're going to be trying to do with RF excitation. And here's the idea that up to now, we've sort of implicitly be talking about non-selective excitation, which is a sense that we apply this RF pulse and all the spins that see it will tip over. Okay. What we'd like to do is figure out a way to do what's called selective excitation, where we only excite spins within some specified region. So what that looks like is, for example, if this is M sub Z and this is MXY, before excitation, all the magnetization everywhere is at equilibrium. So M sub Z is equal to M0 in this case. After the excitation, you notice that the M sub Z component goes to 0 in some slice. And so basically all those spins have been tipped away and all their magnetization has gone onto the transverse plane. So that's my goal, our goal for selective excitation. And then to give you sort of the concept behind that, these are the last 1 or 2 slides we're going to talk about. The idea is we're going to just use a gradient again. So this is the slice direction. Let's say this is the Z direction here. So by convention, slice direction is always the Z direction. And we want to excite a slice that has width delta Z, okay? And so the way we do that is if we have a pulse, an RF pulse, that only has frequencies within that band. So this slice here, is at minus delta F. This is at delta F. Okay, so I have some range of frequencies here that I want to excite. So I want a pulse that has a frequency for this guy, a frequency for this spin. Each spin wants to see a different frequency. So I'm going to have a pulse that has those frequencies in it. Okay, and so that's going to be a rectangle function in the frequency domain. And that turns out to be that means I should play out a sync pulse in the RF domain or in the time domain. And so that's going to turn out to be the answer we'll see on Monday. So the last slide that I want to go over is this movie here, which is just sort of getting this point across, where we have different pendulums here of different lengths. Okay. And then this is the driver pulse. So this pendulum, as you watch the movie, that's going to be what's going to start, that's going to be set in motion. And then we're going to start to see which one of these other pendulum also goes into motion. All right, so let's play the video. So at some point in time, let me see when he's going to pull the pendulum. Okay, so now he's exciting it. So he's going to set that pendulum in motion. So notice that initially everything starts moving a little bit. Okay. But over time, you notice that only this one here has a large amplitude. Okay. So basically, the RF pulse the driving mechanism has some frequency. And so by the different lengths of those strings is similar to what we have with an MR gradient, where each ball has its own frequency. And then if we excite within the presence of that gradient, then it turns out that we can just isolate one of those pendulums to excite. Okay, so we'll pick up again on that next Monday. Just a few logistic notes. So I will be posting the next homework either tonight or tomorrow morning, and also probably the next pre-lecture quiz at the same time. So just make sure for the pre-lecture quiz, it's always good to just make sure you have enough time to review the material before you do that. I will stay here for office hours for a little bit. If anyone has questions, or if you have questions about, for example, project topics for project 2, remember those are due this Monday. Okay, so we're going to stop the recording now, and I will stay here for additional questions if anyone has them.